Hey, welcome back. And we're now going to kind of look at our next effect, and that's latency. Remember that in the previous lessons, we looked at exceptions as an effect. So we wanted to kind of enhance our types to reflect the fact that a computation could fail. But there's another effect that we want to make visible, namely the fact that a computation can take time. And that's what is going to bring us from the top left to the bottom left. So we're now going to go from trie of t, and we're going to introduce future of t as a monad that captures the fact that computations take time. All right. Let's go back to our simple adventure game where we had collect coins and buy treasure. And then we had this kind of little script where we first collected some coins and then we bought treasure. So what we're going to do is we're going to morph this little adventure game into a networking script. And it's really easy. So first of all, we're going to kind of, turn our adventure into a socket. And instead of collecting lists of coins, we're going to read from memory an array of bytes. And instead of buying treasures, given a list of coins, we're going to send a packet from the US to Europe and back. All right? But you see that the signatures have the same shape as our little adventure game, and our little script even looks the same. We're first creating a socket, we're reading from memory, we get an array of bytes, and then we send a packet to Europe and back. By now, you know that while this code looks easy, it's not as easy as you think. And the reason is that reading from memory takes a lot of time, and sending a packet from Europe and back takes even more time. But this time is, expressed in nanoseconds or microseconds, which is not very kind of intuitive for humans. So let's look at kind of a little table that tells us the time that various operations take, on a kind of computer. Note that these times, will vary because computers are changing. So take this as a rough guess. All right. So taking, a typical instruction, 1 nanosecond, but let's look at this. We're going to read from memory, so that's 250,000 nanoseconds. And sending a packet from the US to Europe takes about 150 milliseconds. And notice that a lot of these times are limited by the speed of light, so we cannot do much about them. Now, I don't know about you, but for me, I have no clue what 150 milliseconds means or what 1 nanosecond means. So let's take these numbers and take 1 nanosecond and turn that into a second, and then we kind of calculate weeks, months, and years from that. All right, because this thing does it still. They say, read from memory takes 50,000 nanoseconds. Who cares? All right, so let's kind of change these numbers into something that we, as humans, can understand. Okay, so 1 nanosecond becomes 1 second, and then we'll turn that into days and hours. Now we get a much better picture. So in terms of human timescales, reading 1 megabyte from memory takes about 3 days. Okay, so it's like sending, your kid to do some groceries, and it takes 3 days. They have to go on their horse to the next village, get the groceries, and come back. And of course, this can still fail. So when you're kind of, driving your horse to the next village, there might be bandits that, attack you. So it doesn't only take time, it can also fail. But we dealt with failure in the previous lectures. But this one is even worse. If you look at the sending a packet from the US to Europe and back, in human times, that takes 5 years. Okay, so underneath that simple program, was hidden some enormous latency, some enormous time that this computation took. And that was not visible in the type. So let's make that again visible in the type. Because we don't want this reading from memory to block for 3 years and then, also for 3 days, sorry, and then sending the packet to Europe and back will block for 5 years and only continue when there's no exception. If you look at in real life, when we communicate with people, imagine that you would ask a question to a person and it would take 5 years before you get an answer. You're not going to wait 5 years. What would you do? Well, what I would do is I would give this person a self-addressed letter. I would say, here's the question. I know it takes 5 years for you to answer it. Once you have the answer, you just put the answer in this envelope and you send it back to me. That idea in computer science is called a callback. And that's exactly the mechanism we're going to use. So if a computation takes a lot of time, we're going to introduce a type where you can register a callback that will be invoked once this computation terminates. And again, that computation might terminate successfully or with an exception. But let's first show that we as humans are still superior to machines. There's now a lot of talk about, the rise of AI and that, we have to be really scared of computers. But I don't think that's that bad. Because apparently somebody has swam from Europe to the US, and that kind of, took about 3 months. And if you want to walk across the continental US, that takes about 12 months. So if you cannot make the same journey that that packet makes, it means that humans are still twice as fast as computers. So I wouldn't worry too much for the machines to take over. All right? But here's the question. Is there a monad that we can use to express the fact that computations take time? Well, after the break.